Let's start. So today I want to walk you through how to run semantic search directly on a data lake without standing up a separate vector database or without copying your data anywhere. So this is part two of our two-part series. In the first part, we covered full text search on Iceberg. Today it's vector search and semantic search. It's the same idea that you have your data in the data lake, and we are going to search it right where your data is. Fresh as new row lands. With your SQL, you can combine your SQL filters and counts in the same query. So let's dive into it. So why? First question is, why do we need vector search? So we'll just go through the primer. Here is a real example. Let's say there is a support engineer who's searching for databases ran out of connections. The ticket that would help him says that Hikaru pool 1 connection is not available. A request timed out. Same problem, not a single shared word. So they don't share the keywords. So keyword search never finds it because keyword search needs matching words and stemming can't close a gap that big. So embedding provides a solution to that. They put the relevant or the closest word close to each other, same meaning, different words. And when you run the vector search, you find those matching words or matching rows. And that is why we require vector search. And so generally we use token matches, and then there is a concept of dense vectors where the same words or same vectors are put together. So the question is, the data lake was built to store a lot of data cheaply. So we all know that we use object store we for data lake, and we store all our data there because it is cheap. But it was not built for search. So we really have a couple of choices. Copy them into search store, copy the data from data lake, copy them into a search store, embedding it shift to a separate system and kept in sync by a pipeline. So you have a ETL pipeline which is doing the copy and making sure that both the copies are in sync. The second choice is you scan the data lake and there is no indexes. So it is going to be slower. And the first choice, where we have two copies, you have to maintain two systems, you have to ensure they are always in sync. With a scan, you can run search, but they are always going to time out or going to take a longer time. So what is the third option? So third option is basically index them where they are. So you don't do a copy, you don't do a scan. So you build an index on the data lake itself. So what it enables you is you can drop the pipeline and you can still do the searches very fast. So it avoids the two system complexity. So let's do a quick. So what are the advantages of dropping the ETL pipeline? So the results will be faster because you are not scanning, and you can do your searches in a sub-second or faster. So there is no, and as the data lands in, it is fresh. There is no ETL pipeline to sync. You can also combine other analytics with your searches, like you can do filter and count in the same query. You don't have to hand off this analytics to a different system. You don't have to touch the files stays in the data lake as it is. You open the, and we just open the parquet file, and you don't need everything in memory. So you don't have to spin up a large cluster and fit everything in memory. So before we dive into how do we enable vector search on a data lake, let's take a look at what vectors are, what are different indexes are available. Just a quick primer. So, uh, so it is a very simple idea. There is an embedding model which takes your ticket or data associated with it, and it turns into a list of number. Text me that means the same thing end up closer together. So every ticket becomes a point in a space, and similar tickets sit near each other. Second is, how do we measure nearness? Like, what does it mean? Like, the two sentences are near. So there are few ways. So there is a cosine which looks at the angle, usually one for the text, and the honest answer is that numbers are normalized. They all rank things the same way. So the model you pick matters and not, and the whole foundation is that you choose an embedding model, and using that embedding model, you create a vectors, and then you use an indexes to find out uh, what are the closest words which are similar by the meaning. So what are the choices to find out the closest? So one is you can use the exist canon, which basically is a scan based. So you touch every vector, every query. So as you are going to scan all the data and you're going to read all the data in object store or a data lake, so that is going to cost as well as not be very performant. So the second choice is you can use sort of an approximate neighbor, nearest neighbor indexes. So it how it works is it like kind of a hop a handful. It just uses a graph mechanism and follows a few links to the right neighborhood instead of visiting everyone. So you can do the searches faster and you don't have to scan the full data. So next question is, what indexes are available? So there are few familiar families of these indexes. A graph like HNSW, which hops from rough to fine and give you the best recall for the speed. Then there is a partition and compress. You only look at the nearby groups and you store short codes instead of full numbers to save space. There are also trees and hashing, which were popular earlier but don't hold up as the dimensions grow. The short version we can think of as we use the graph and compress partition. So mostly HNSW is most popular used one. And now we are going to see like how do we push that one step further and run these indexes directly on top of object store. So as you can see, you can keep all of it in memory, keep it in object store. So next question is, what makes vector search hard at a scale? So there are four things. So first is memory and cost. So a full vector on every row, the index piles on more. And if we have to fit everything in memory, the cluster size is going to be huge. So can we keep it in the object store? The second question is rebuilds. So do we rebuild the whole thing or do we do the incremental build of the indexes? Uh, the third question is filter. Can we apply other type of analytics or other type of filters as part of the query execution along with the vector search? The last question is, can we do, how fresh the searches are going to be? Is it going to, what is the lag? So can we enable the searches in near real time? What does mean is as soon as the data lands in your data lake, are you able to search for it or not? So next question we had was, so should we build one a big large index, or should we divide into a sub indexes based on segments? So think of segment as a fundamental unit of your data, which you can use to query or partition. So if you build, what are the pros and cons of building global versus per segment? So if you're building a global index, so you every time you'll have to update, you have to lock it, and queries will have to wait for the index to be rebuilt. And and when you build it per indexes, then you can independently build those indexes, and your query can run in parallel. So obviously you lose little bit of correctness, or you have the recall penalty, but that is given at the data size, that is okay. So in our scenario, what we have gone with is the approach of building the indexes, vector indexes on the segment, so that we don't lock. So writes are happening as soon as they land, and basically indexes are built as soon as the writes land in the data lake, and queries can also run independently. So next question is, what did the segment bit buy us? So it is a lock-free ingestion. So there is no lock while the ingestion is happening on the data lake. We are able to build indexes independently. If you delete certain segment or certain data sets, so only associated segments are going to be deleted. So you don't have to rebuild the whole index, vector index. And the third is like you can build a tiered storage mechanism on top of it. So the hot segments will always be in memory or on the local disk, and the cold segments can be tier to object store and bring it back based on the query requirements. So how it works? So as soon as the data lands in the streams are landing in a data lake, or let's say if we are running in the real time table. So basically we create a consuming segment which kind of creates a in-memory version of the vector indexes. And once that consuming, once we have one based on certain criteria, based on a size or a time, we seal the segments and we call the seal segments. And then when the segments are sealed, then it becomes a offline segment. And either we so whatever data is in memory can be searched from the consuming segment, and whatever data is sealed, it can be searched from the object store. So how do we express a vector search in our system? So it is a similarity function in where clause where you can specify a filter. It returns a set of candidate rows. The ones in the neighborhood, you can combine it with any filter using and ranking happens in the select. We measure the exact distance on just those candidates and then order by it. You bring the query vector number is how many results you want. And you can see a sample example where we are searching for a ticket ID column, and we are trying to find uh, vector similarity index on an embedding column where vector indexes are stored. And you can run other SQL function or operators as you require. So So the question is, now you're combining analytics and the vector search. So do you do filter first or search first? So if you filter after the search, you ask for 10 results, might get one or none. If you filter first, then check every survivor by hand and you get the right answer, but you have thrown away the index. So the right way is to let the engine decide based on how selective a filter is. Loose filter, do the search, then filter. Very selective filter, just scan the few rows that are left, and one engine can handle both for you. So you can apply the order in which you want, and the smart and basically you can combine both, or you can say that, okay, I want to filter first and then basically search, or you can run the search first and then filter. So you can change that order in your queries. So the next question is, we know that vector indexes can be huge, and especially given they are on data lake, so we cannot fit everything in memory. So how do we solve the problem of the search? So this is where our segment based approach comes in, and we have a tier storage model. So we first identify what segment or indexes we need to read, and once we have identified, we can keep them or cache them in based on how frequently they are accessed in memory. And then the second tier is local disk. We can also cache them in a local disk, and the cold section is always in the object store. And this tiered cache is maintained based on the access pattern of the queries. So whenever the queries comes based on certain criteria, they are cached in memory or tier to disk, or keep as it is in object storage. So what it helps is, without a very large footprint of nodes, you can still run vector search very efficiently. And you can also tune these parameters if you want very high latency, versus if you want where you want to save the cost, where latency is not a concern, versus where you want it to be a very fast latency is a concern. Then you can have more cache and the searches will be much faster. So we all know, like, object store was mostly started with a sequential access. So in vector search there is a lot of random reads are happening, and in the vector indexes, when it is created, creates a bunch of small files and then it hops across. So a lot of random reads are happening. And we also know that object store many small reads will hurt you, like they will always pay a round trip latency. And one of the thing is, in because graph walk is happening in HNSW, it is hopping from one offset to the other offset. So when you are building vector search on object store, you need to ensure that you solve all these problems and basically make it performant, both from cost perspective and the latency point of view. So how do we do it? So basically we use Lucine's HNSW library, a vector index library. So Lucene creates a lot of these small metadata files and the index files. So we first thing we do is we combine all of these multiple objects into one, and we create a map of offsets where each metadata is kept. And then when we bring, or when we are touching the segment, or when we are reading this segment, so we create a metadata cache locally, and the metadata cache is tiered, so that what offset of indexes we have to bring or read, we are aware upfront, and then we can directly go and fetch those byte ranges from the cloud. So that will not only make it performant, but it will also fetch the bytes which are required, so we don't do a wasted read. So let's see at a high level how the architecture looks like. So so basically we have the external table where we have created the table. So whenever the query comes in, so we have broker where the query lands. Then the broker, first thing it does, it prunes the segments which are not required as part of the query. Once it has identified all the segments, then it will hand out the segments to the corresponding servers, or the servers which owns those segments. And then each server will go through its own cache layer, where it will find out whether the metadata or vector index or the data is cached or not. And if it finds from the cache, it will return from there. Otherwise it will go to the source bucket or the data lake bucket to read the data. Or we also have our own managed bucket for indexes. So for index, it will go to the managed bucket index. So so both data and the indexes which we build lives in cloud, and like data is always in the data lake, the indexes in is in the bucket managed by us. And we each server maintains its own local cache whenever the query comes, so it can leverage that. So with this approach, we are able to make sure that whenever we have to rebuild the indexes, we are able to do independently without touching the source data set. And these indexes are built inline as soon as the data lands in. So we get a notification and the indexes are built. And with this approach, the same engine can apply your analytical plus the vector search on your data lake in a single query. So next is like, how do we build these indexes? What is the workflow? So we have Iceberg catalog. So we from Iceberg catalog or any other like for example, Iceberg or a Delta table. So there is a watcher task running which monitors if there are new snapshots available in the Iceberg or a Delta table. And as soon as a new snapshot is available, the watcher hand over to the indexer. And what it does is it basically enumerates all the data set in that snapshot, find the diff against the last snapshot which was onboarded, and build the indexes for the new data set. And it also creates a lightweight metadata in our system for each of the Parquet file in the data lake. And this metadata is leveraged during the query side. So we can do the pruning, and we can use the statistics to find or filter the data set faster. So this is the high level workflow. Just to reiterate, watcher finds the diff in the catalog, enumerate the data set, the differential data set. Indexers start building the indexes on that data set, and metadata is the one which ties them together, which enables pruning and building statistics on the for filtering and other purpose on this data set. So let's take a look at like what makes it faster at data lake size. So first thing is the pruning. So in a data lake, you can have millions of files, which corresponds to millions of segments in our system. So if a query comes, if you're going to scan or run across all the segment, it is going to take a lot of time. So first thing you need to do is, based on the query, can we prune those segments? And then the second is, can we parallelize this searches across segment? So that is a server level parallelism. Then the third is, can we pin these hot ranges or cache those hot ranges which are frequently accessed, metadata as well as the data layer. And if there are misses which are not available in our local caches, can we parallelize them in parallelize the request so that we are able to leverage the full pipeline from the object store. And the final is, can we do the prefetch ahead? While a query is working on, let's say, 10K records, can we prefetch the next 10K records up ahead so that CPU is always busy? So we apply all these techniques. We start with the pruning, hand it off over the segments to the servers which own, so that parallelism can be achieved. Then we also have the caching, where we cache the hot data ranges. Then if there are misses, those misses are fired parallelly. And then we also have the prefetch. While the query is working on set of records, the next set of records will be all prefetched, and we create a pipeline. So all these techniques let us run any query against data lake, and if the indexes are enabled, within sub-second latency. So let's look at one segment at a time. So in the segment, we have the vector index. So basically, we walk the graph. So there are a few hundred hops. Then there are the top candidates, top key rows, and these are all identifies as a bitmap. And then we apply the filter if there are any filter. And then finally, whatever the records are available, those are the final records or the surviving records in the query. So similarity or vector similarity also is a filter in the SQL query, and that can be combined with any other filter predicate or operator you have in the query. And then the column where the data is are read last, which is like, you only read the data you need, so you never do the vested read. So so this is one sample query, where you have vector similarity search. You are also searching for which plan, and you have the timestamp predicate. And you can see that in the output that you find that EU West, US East. So the tickets were like in all these regions. So you're able to identify how many tickets related to your search or related to this embedding was available in different region. So take a look at the demo. We have vector search demo where we have used MinIO for so we have Iceberg data lake, but the backend is a MinIO, and then basically on top of that we will enable the vector indexes, and then we'll run the vector search query, the one which we just saw. So let me just play the demo. So you can see that this is the Parquet file where you have an embedding column, you have category column, and this is just showing the content of the Parquet files. And these Parquet files will be uploaded to object store. And then this is the Pinot schema. So where we have dimension field spec, matrix field skep, and this is the table config. And the last section shows how the vector index is enabled. So there are different configurations. You can configure what is the dimension, vector dimension, what is the vector distance function, and yeah. So this is the metadata of the segments, the lightweight segments which are created. So which is pointing to the object store path, and also store some metadata associated with it. And this is just going through the internal metadata, how internal segment metadata looks like. And the segments are stored in the bucket which is managed by us. And now we run this query. So this is just giving us the category column and how many counts were identified. Now let's take a look at run using the vector similarity using the embedding. Yeah. So and this is just showing the explain plan. So you can see in the filter operator, we use the vector similarity index and the arguments to it. So it's just running more filter operators and the query. Yeah, so now you can see that you can run the cosine distance or distance functions on the columns itself. And cosine distance is run on the embedding column, which stores the vectors. Yeah, this is another where you are comparing the vector similarity radius. So yeah, so this is the demo we had. So moving on. So next question is what is the cost of building these indexes? So first cost is the storage. So there are different options based on what kind of index you choose. Index size vary, but we provide these capabilities. So there is HNSW float 32, which is like if you're indexing 50K docs, so it is comes around 140 MB. So this is just a benchmarking showing which compression technique or index to use to reduce the vector index size. If you are using IVF product quantization, then it reduces to almost 25 to 50 times. And it can help you save storage cost in the object store, and it also helps in while we cache on the local storage, local nodes. And the next is basically the latency. What latency do we get? So if you're not using any vector index or full scan, so this is only on one like couple of segments, but if there are like very large scale, this number can go much higher. So if you can see full scan, it is almost like taking 103 millisecond, versus when you do vector index plus SQL filter. So basically, practically it is the same, like which is 50 millisecond, and twice as faster as doing the full scan. And this is directly from the it is from the object store. So you can see that adding SQL filter can be parallelized, and it's not adding too much cost. So next is basically how the caching helps. So when everything is like local, so then the query becomes much faster, like it is everything is cached. 22 millisecond when everything is pinned. When nothing is pinned, everything is remote, including the data, and which is 110 millisecond. And then if you have remote plus pinned, so some of the data is pinned and some of the data is still remote, so the latencies you see is 32 millisecond. So that is where our caching comes in. Like we don't cache all the data, we cache whatever is required, and it improves the performance. So it gives you best of both world. So we saw that we ran the vector similarity, and vector similarity, you need to specify the vector embedding yourself in the queries. So the question is, can we do better? And that's where the semantic search or semantic match comes in. The idea is, because you will have to construct those embedding using your embedding model outside of these query engines to use the vector similarity. So what we said is, like, can you run the vector semantic search directly into the query itself, and into StarTree cluster. So what you can do is you can use a semantic match, and what it does is you can specify what you want to search, and you can plug in your own embedding model, the one which you use to create the vectors, and it will internally create those vectors and run vector similarity for you. So it simplifies the further operation, and you have a choice to plug in whatever model you want to use. So it rewrites the same vector query into more like a text query or a full text search, where using the semantic match. So here is the demo of semantic search. It is in the similar lines. It just is the same data set which we saw in vector search query, and running on top of object store. So as you can see that search has evolved. So it started with a text search where it is giving the full text search. Then you have a vector search where you can specify the vector embeddings, and then the semantic search where you can provide in plain English, and the underlying embedding models will create embedding for you and run the vector similarity on top of it. So the query path looks something like this, where you have semantic match query, which uses the embedding model to create vector and then run internally the vector similarity. And you basically can have the configuration where you can specify what columns you want to bind per embedding model, or you can have multiple embedding models across columns. And this is the sample data set. So this is just running plain analytical queries, and then we'll see how. Yeah, so this is where the semantic match is happening, where we are running headphones for a long flight. So it returns the noise cancelling headphones. The similar thing, like safe place to backup family photos. Yeah, so these are a couple of semantic match or semantic search queries. Yeah, so now here you can see we have combined the filters, other filters, like you can say rating is greater than 4 and 4.5, or price should be less than 200. So combining both gives you much better results or more crisp results. And the final, we have the explain plan. Like, how does the explain plan look like? Yeah, so this is what semantic match or semantic search can um, provide you. And the good thing is you don't have to copy the data. You can run the semantic search where your data sits, which is in the data lake. So what are the key summaries or key takeaways? So the key takeaway is search where the data already is. So you don't have to copy. There is no ingestion, there is no ETL pipeline which you have to manage. and index keeps up. So index is always up to date. So as the data is landing, indexes are getting built. You also have the choice to add or drop indexes as you would like, and that can happen in asynchronously. You get the advantage of having everything in object store, so you obviously it is cheap, and for as you require more uh, better latencies, you can pin or cache the data more or throw more hardware to it. And you can run all the things like similarity, hard filters, and aggregates, or including joins, everything in one system. You don't have to spin up or stitch three systems together. So basically, stop copying data to search it, and stop choosing between finding things or counting them. So you can do everything in one engine. So where to go next? So this is part two of the series, and this is a two-part series for building a search on a data lake. Part one of the series was full text search, which the webinar is already out, and you can see on our StarTree website. If you want to try it on our table, you can try it out. There are docs and deep dives, which we'll share in the chat, the links how to get started, how to try it. And time for questions, so we can take some questions we have. So I'm not sure how many folks are using or building search on a different system, or they building search on a data lake itself, and what are the use cases they have seen. Would love to see any responses on the chat if you have. Because as the data is growing, I think one of the challenges is maintaining multiple systems to do certain things. So the goal is, can we combine and have one system of record where we can run um, search analytics together. Yeah, so we have one question, which is if this is a use case others have seen. So yeah, we are talking to few customers where we have seen that they want to kind of combine, or they use the search along with the analytical queries. So they want to combine, and they want to see the results in a single place. So we are seeing that. And the second was like, what do you folks use today to? Yeah, so other question is, does this work with the both real time and offline data? Yes, it works with both real time and offline. So you can have a real time. So you can have a real time table, which can write into your Iceberg table, and then you can query from that offline table as well. So you can have a combine or hybrid table approach. So that works as well. Next question is, can I power a user-facing application which needs semantic search capability? Yeah, I think that's precisely the use case, one of the strong use cases. And I think the user-facing application require they are very latency sensitive. And we all know that semantic search can help greatly build a search in your user-facing application. And if you're building it on top of object store, you need to ensure that latencies are in acceptable range. So this definitely is our is one of the use case which strongly works on us, because we can ensure that the search latencies are sub-second, and user facing applications can leverage that. Yeah, other question is, what about the agentic workloads? So yeah, I think agentic workloads also, because they rely heavily on the RAG systems or the searches. So those systems can also use StarTree for not only doing the searches, but they can also use it as a memory store, where they can store the short-term memory or the short-term context, and get advantage of it. So yes, I think the user-facing application which requires semantic search, agentic AI workloads which require um, faster searches at a scale. And the third use case could be the AI observability, where you want to bring a semantic search meaning into it. So that can also, you can basically filter your logs or AI observability logs not only by keywords but with the semantic meaning as well. And you can also combine analytics with it. So that becomes very powerful. Yeah, next question is, do I really need a specialized vector DB at this point of time? Uh, I think the way most of the databases are adding the support for a vector search. So I think uh, analytics, search, and vector all are getting combined. So managing three systems versus managing one is always easier. So uh, the shift or the trend I'm seeing is more specialized databases are bringing the vector search in as a first class region. So you really don't need a vector DB at this point of time. What you need though is you need to build the AI pipelines. For example, plug in your own embedding model, run some AI function natively into the database, so that reduces the complexity of building the AI pipelines or managing extra infrastructure. And we do support all of those. So I think if if you are running a AI agentic workload, or if you're running a simple search, or you're running a search plus analytics, or if you're running vector or semantic search, we support all of them, and we support at a scale. We also work on top of object storage, so basically cloud native, so it can save cost as well as be performant at the same time. We'll wait for a few more minutes for any new questions, and then we can wrap it up. So if you want to get started with the StarTree Lakehouse, so here are quick start. Basically, we have a form where you can fill up your workload and the timelines. Supported data, so we support Iceberg and Delta Lake both, and you don't have to do any migration. We can connect your existing catalogs or table format, and enable enable a static query engine on top of it. And it is proven performance, already been tested and validated at a couple of places. You can bring your own workload, validate your own workload, and you can define the outcome. If you want to try it out, you can reach out to the email which is shown, chinmay@the startree.ai, or you can browse the startree.ai website, where you find a lot of resources and material. So this is the quickest way to get started. And I think we don't have any further questions, so I'll wrap it up. Thank you everyone for joining. I hope you enjoy this session. And if you have any further questions, so reach out to this email address or reach out on our website, or through LinkedIn. Happy to collaborate or answer any questions you have. Thank you.